lesson I'll do is a quick review for you. I was talking about Newton, and we're talking about the fact that Newton... No, I was talking about Newton.
It's on recording.
It is on recording, but that's all right. What? I'm going to expand that. I'm going to close this. And then when I comment on students who are doing the wrong thing, I will post them a copy of the YouTube and explain what they were doing at the time. So, what we had was the Earth with a hill on it, and we comment on the fact that Newton said that if you just fire, this is out of sync a little bit, if you just fire at it with increasing velocity, it will go further and further until eventually you'll get to a speed where it will orbit. And we calculate out that speed. And you need to remember how to do that. So, that's the way this one works. No. So, yep. So if you remember, because the force of gravity is dragging downwards, you need an equivalent circular force acting against that. So we said that Fg equals Fc, the centripetal force. And we find that one side, that's G large M little m on R squared equals mv squared on R. And if you rearrange that equation very quickly, I'll swap it around the other way. Let's put v squared on that side equals, and you have the gmm R squared there, and that will become times, as you swap the R over, R on M. And of course what you find out when you do that is one R cancels out for the R squared, that M cancels out that, which means you end up with the end of formula, which was that the orbital velocity is going to be the square root of G large M on R. And what we did comment on was the mass of the planet and the radius you are from the center of the planet are the things which are important in working out the orbital velocity around an object. And we did find out that it was about 7.9 kilometres a second for the Earth.
So would we be able to write up some notes?
We are writing up some notes, and I've got some notes ready to go. So what I'm very quick to do is just revamping, because I lost my podcast. The other thing that you should note with it is that this formula works in other contexts as well. But it is the orbital velocity, it's not the escape velocity. Orbital velocity is simply the orbit of the speed you need to go and orbit around a massive body. It doesn't allow you to go outside of its gravitational field.
So if something was a lot more than that, would it just every time it goes round create a larger orbit and eventually go out?
If it's a lot more than that, and very much more than that, what it will do is it will end up going up something.
A lot more than that, just like a little bit more.
A little bit more. Yes. Yes to the answer. Now, in a past HSC, the 2012 HSC, yeah, oh no, I'll just go down to the question I'm after. There's a rather interesting question which actually relates to this. And we're about there. One of the interesting things that they do have, by the way, which relates to this topic, is you have up here, outline a first-hand investigation can be performed to measure a value for acceleration due to gravity. And we've all done that as the pendulum prac. But you notice these questions. How do you assess the accuracy, the reliability of the data collected, and increase the reliability and assess the reliability? So you actually need to know a little bit about prac design to do that. But the question I really want to look at is this one. Here we go. I'll just make that a little bit less zoomed because you can't see it. So there's the question. It says this. Question 23 from 2012. Consider the following thought experiment. It might be more than the thought experiment one day. They're actually talking about building space elevators. 2 towers are built on the Earth's surface. The height of each of the towers is equal to the altitude of a satellite in geostationary orbit about the Earth. Tower A is built at the Earth's North Pole, and Tower B is built at the equator, and they've got a picture of it there. Identical masses. It doesn't matter what size the mass is, but identical masses are simultaneously released from rest from the top of each tower. Explain the motion of each mass after their release. When you look at the question about this, you'll note a couple of things about the question to be able to answer it. What's the first thing you should note in the question? That helps. So you've got identical masses shown there. Yep. Yeah, they're all important points, but what's the verb that you're trying to do? Explain. That's the thing there. Explain means, in science we have a very particular way of looking at explain. It does occur for everywhere else, but it's cause and effect. Normally in these questions you talk about the other way around. What's the effect? Why does it do it? So in here you have 4 marks. So they're going to expect to see from you what happens at Tower A and why, what happens at Tower B and why. You need those 4 parts of the explanation there clearly. Okay? Which way is the Earth rotating in this, Cody? Yeah, exactly. Which way is the Earth rotating in this diagram? It's going to be a very long blank bit on this.
It doesn't tell you.
It does tell you.
East.
You want to go that way. There's the equator there. So I'll spin with the equator. Will it go from right to left or left to right? That way? It'll go this way.
That's just the rotation here.
Because that's where the sun rises.
So what's that?
So that's east, that's west. Okay. So this tower is basically spinning on its axis. This tower is moving around with the surface of the Earth. Right? Okay. Let's see. Riley. No. Riley Anderson. Tower A.
That's it.
What do you believe will happen to the masses dropped from Tower A? It will fall. Which way will it fall? Towards the pole, or where it is? So you're saying it will go that way towards the centre of the Earth. That's really horrible. But anyway, okay. Why do you believe that? Because there's a force of gravity which is acting downwards in that direction. Not a problem. And it's spinning on its axis, right. Okay, so Josh, you can... Not Josh. Here's Josh. Josh, what do you think is going to happen at Tower B? So which direction is the mass going to go? That way. So you think it's going to go sort of in a curve like that?
It's hard to explain that on a 2D. But he reckons that it will come towards us. If you throw it...
Oh, it will come this way. So it's going to come in a rotational direction out like that.
Depends which side of the tail you drop.
It won't be moving relative to space.
It'll be moving relative to Earth.
Okay.
So it will just drop straight.
You know what it does? What does it do? It
stays with the tower.
It sits where it is next to the tower and continues to move around with the tower. It goes in orbit with the tower around the Earth.
What if you go on this way, falling this way, roll it that way?
Did you say throw it or leave it?
No. Are released from rest,
Yeah.
dropped.
If you just do that.
So the critical part is that from rest is the really critical part of the question as well, which we didn't pick up. So because this thing, as the height that a satellite would be if it's in geostationary orbit above the Earth, in other words, it stays in the same position above the Earth, its velocity happens to be the right velocity so that the mass just sits there with it, also in geostationary orbit.
What? It would just stay there.
It would just sit, you'd be in that tower, it drops because it's spinning on its axis basically, or actually fall down under influence of gravity. This one, you're on the tower going that way, you hold your mass, you let go, and it will just keep going with you. And you'll say, that's interesting.
What if you throw it or drop it? So,
If you throw it, right, and you add some velocity, if I throw it hard that way, it'll go a little bit higher. If I throw it that way, it'll go a little bit lower.
what if you're rotating
That
this
is,
way,
velocity will change.
and you throw it that way, it won't have as much speed as you do.
We're going, when on this diagram, the tower's moving into the board,
Yeah,
rotating
so
that way.
throw it away from the board, wouldn't it?
It will drop a bit, and it'll change. Yeah.
To drop.
You'll only give it a set velocity, and so it'll drop a bit below the tower and then probably stay there.
So that means it's also speeding up a bit.
No, it doesn't speed up again.
Well, if it's got, if it's
Oh, I see what you're saying, yeah. It gets to the right velocity to stay in orbit.
How could we determine that from Tower B that object would stay stationary? Because you don't have the height of the towers, and therefore you don't have.
You are told the height of the tower. The height of each tower is equal to the altitude of the satellite in geostationary orbit. You do have it. You have to read the question.
I thought,
That's why it's an interesting question. Okay, that will do for this little section.
So really,
Okay, so we've looked at orbital velocity, which is distinct from escape velocity. And escape velocity, simply put, is if you have the Earth and you have an imaginary boundary for its gravitational field out here somewhere, if you want to launch a rocket from the Earth beyond that, where it is practically free from the Earth's gravity field, you need to have a certain speed, which you call the escape
So
velocity.
his famous
Now-
book or whatever you wrote here, is it Principle of Mathematica or just Principle?
Oh, it's known as Principa, but it's actually the whole name you just said, yeah.
I think Principle of Mathematica.
Yeah. So this idea takes quite a deal of imagining to work out how we do it. But what we're going to do to work out our escape velocity is we're going to think about energy. We're going to think about the gravitational potential energy versus the kinetic energy of an object. And we do that with a good reason. Imagine, if you will, that I take my pen and I throw it now with enough force, do enough work on it, so I've accelerated enough so it leaves my hand, goes up 1 metre and comes back down. When it goes up 1 metre, what has it gained? It's gained potential energy, hasn't it? So I've done work on it, it's been accelerated, it reaches a certain height above the Earth's surface, so it's gained gravitational potential energy, which is measurable. What was transferred, no guys, what is transferred or transformed into that potential energy? Kinetic energy. Yes, you did. Knowledge, I want everyone to do it. So by accelerating it, I've given it a velocity, and it is accelerated then downwards by gravity. So I've done work on it. Okay, that kinetic energy that it has is exchanged into potential energy, and then it comes back down again. If I do more work on it, accelerate, put more force, accelerate it harder, or with a larger acceleration, what will happen to its height?
go up higher.
Go up higher. It will gain a bit more potential energy, and it will come back down again. If I do it again even harder, it will go even higher. Now you can imagine that there's a boundary at some point where if I get the object just below it, it will fall back down to Earth under the influence of gravity, and it will only just be accelerated by gravity. But if I go on it, so the centre of mass is right in that line, it has just escaped the gravitational field of Earth. So what does it do there? just stays there. If you go just above it, it will just continue to keep going. At that point, if you can imagine that line, is a point where the potential energy
So will it move or does
equals the kinetic energy. So if I give it enough kinetic energy, it can actually get to a point where it'll just be in this gravitational field, and then it'll slowly come down. If I give it just a little bit more, it'll go beyond it, won't it? So what we do is we put the, yes, we can. So if I put these formulas in, we know what the formulas are for these, don't we? Potential energy on this side is this formula that we used, because we're taking into account the fact that as you go higher and higher, the acceleration due to gravity decreases. And on this side of the equation, we know that it's a half mv squared on r, because it's potential energy. It's not the force, it's potential energy.
If you put it onto that line, will it just sit there like that?
Well, there's not really a line like that, but theoretically you get to a point where you get enough kinetic energy that just gets to the edge of the Earth's field.
How far away is that?
Well, we'll work that out one day for you. So, rearranging this equation, I can work out what that point is for any given mass in any given planet. So let's do that quickly. I'm going to put v on this side, or v squared on this side, because that's the subject. So it goes on the left-hand side, which means I'm going to have the original equation, G m on r, and of course, to get rid of this half there, I need to multiply by 2, and then I'm going to do some divisions. What am I going to divide by? M, which means that m and that m will now cancel, which means that I now have v equals the square root of 2gm on r. That's our escape velocity. Now you'll notice that compares to our orbital velocity formula of gm on r. So they look similar.
Right, so does that mean you have to be going twice?
No, not twice. If you can actually change that using the third rules. So you have to be going square root of 2 times faster than the orbital velocity.
So pretty much all the 2 does just pretty much says a little bit faster than the orbital.
But how much is a little bit faster?
7,900.
No, it's not.
How do we explain that? Ah, take that.